Okay, gonna start a new problem today. This problem goes like this. We have y times dx dy, and then we're gonna subtract x, and that is equal to 2y squared. And the initial condition is y of 1 equals 5. Now this one was a little bit intimidating to begin with because I was looking at y squared. You got y squared over here. You got dx dy instead of dy dx. So it was a little bit intimidating. The first thing I tried doing, I wanted to get dx dy by itself. So I decided to divide the whole thing by y, and I got dx over dy minus x over y equals 2y. Now there's a quicker way of doing it, but I'm just showing you my process. Now when I saw this, I was a little bit irritated that I had an x over y here, but I was thinking about combining, how do I combine these two into just one fraction? And I was like, okay, well, if I multiply dx dy by y over y, then I get y dx, and then if I multiply both by dy over dy, you get minus x dy, and then you, on the denominator, you get y dy equals 2y. And I was like, okay, this up top reminds me of the quotient rule. And I couldn't remember exactly. I was like, low d high minus high d low, and then I was like, oh, in the denominator, like, is it the low that's squared or the high? And then I noticed over here I should have divided by y squared all along, just to get y squared in the denominator, because it's low squared in the denominator. So if we do that, we end up with y dx minus x dy over y squared. And then what we can do is just multiply dy on both sides, and we get 2 dy. Then we have it. On the left side we have the differential of, what is it? It's x over y, because if we take the derivative of x over y, it's low d high minus high d low, and all of that over low squared. So then we're looking at just 2 dy on the right side. Now, just like before in my last video, if we integrate, on the left side, the integral of a derivative is the same thing as what you started with, because they basically cancel each other out. That's the fundamental theorem of calculus. So on the left hand side, all we have is x over y, and then on the right we're integrating in terms of dy, so we end up with 2y, and then we of course add c, some constant. Now, what did that initial condition say? We had y of 1 equals 5. Okay, so that just means every time we see an x, we put a 1. Every time we see a y, we put a 5. So we have 1/5 equals, well, 10 plus c. So now we just solve for c. We get c equals 1/5 minus 50/5, because that just equals 10. And you get negative 49 over 5. So the final answer is x over y equals 2y minus 49 over 5. Now that's probably not the best way to leave it. My first instinct is to try and get y by itself, but you end up with 2y squared minus 40. Well, I mean, I guess that's what you want to do. That is what you want to do. You end up with x equals 2y squared minus 49 fifths y. It just looks kind of weird because you want y, you typically want y by itself and then have x be the variable. But this is okay because what we see in the beginning is this right here. We have a dx by dy. It's like flipped over. So if we wanted to check to make sure that we found the solutions here, you know, mainly this is the good one, but if we wanted to verify that, we would just plug everything back in. We have y times the derivative, I'll write it again down here, y times dx dy minus x equals 2y squared. So if we wanted to verify, we just do y times the derivative of x in terms of y. We get the derivative is 4y minus 49 fifths, and then minus x is just this equation right here. So it's minus 2y squared. Make sure to get your signs right. So this would be plus 49 fifths y, and supposedly that's going to equal, I won't put it there yet, but let's see what it equals. So you end up with 4y squared minus 49 fifths y minus 2y squared plus 49 fifths y. What does that equal? Well, we have a minus 49 fifths y, cancels with the 49 fifths y. We have 4y squared minus 2y squared. All we're left with is 2y squared. So that verifies that this is in fact the solution to the differential equation.